Hello, I welcome you all in this presentation related to the subject fundamentals of the manufacturing processes, and we are talking about the metal removal processes. In the last few presentations I have talked about that during the machining cutting forces are generated, and for the machining purpose we need to supply the power to the machine tool. So, the power is consumed during the machining, and most of the power consumed in the machining is converted into the heat, which in turn causes a rise in temperature of the tool as well as of the workpiece. So, because of the rise in temperature of the work tool, temperature of the tool during the machining as well as generation of the high cutting forces, the tool failure is caused by three modes of the failures. One is like fracture, another is the blunting or the deformation of the cutting edge, and this occurs due to the high temperature and which will be leading to the softening of the tool material. And third is the wear of the gradual wear of the tool. So, since these are the three factors which usually cause the failure of the tool. So, if we have to make a tool of particular material, then we will be looking for these characteristics, these properties. So, to avoid the fracture or to avoid the fracture of the tool, it is important that tool material has the desired toughness, which is a combination of the strength and ductility. So, it helps to absorb the load, it helps to absorb the impacts and so avoid any kind of the sudden fracture of the cutting edge. So, if the cutting edge or the tool material is tough, then the catastrophic fracture of the cutting edge can be avoided. Similarly, the another important property to resist the softening, so that deformation at high temperature of the cutting edge can be avoided, which will be leading to the blunting. For this purpose, it is important that tool has the desired hot hardness or hardness at elevated temperature. So, hot hardness is nothing just the hardness of the material at the elevated temperature, and this hardness must be high enough in order to avoid the softening, in order to reduce the extent of softening, so that the failure of the tool by the deformation and blunting of the cutting edge can be avoided. Then the gradual wear of the failure of the tool by the gradual wear, actually it also depends upon the hardness, but apart from the hardness, like the surface finish is one of the aspect. Then the interaction between the workpiece and the tool materials also causes the wear. Then this basically it involves the diffusion of the elements, then the kind of the coefficient of friction or the friction between the tool and the chip or tool and workpiece also affect the wear of the tool. So, in order to have the good wear resistance, primary requirement is that tool material must be hard enough, and apart from this it should have the good surface finish, it should not interact, the tool material should not interact with the workpiece material or the chips during the machining. So, considering the requirement, these three requirements to avoid the failures, it is required that the cutting tool material has the three important properties, that is the hardness, hot hardness, toughness, and the hardness to resist the wear. So, indirectly we can say good wear resistance. But apart from these three properties which are required for the functional purposes, it should also have like desired fabricability or manufacturability, so that it can be shaped or the desired shape can be given, it should be available easily, the material of the tool should be available easily, as well as it should be economical. These are the other characteristics, but the three functional properties which govern the life of the tool as well as performance are the toughness, hot hardness, and the wear resistance. So, considering these properties, the range of the tool materials have been developed over a period of time, and if we see this one, then we need to see what are the materials which are available along with the hardness. Since in case of the brittle materials, of course, hardness can be measured depending upon the hardness of the work material. Different methods are used, like Rockwell hardness on the B scale, C scale or A scale, Knoop hardness or Brinell hardness for the low hardness materials. Similarly, the transverse rupture strength is the another parameter which is used to indicate the toughness of the material which are hard and the brittle. So, this is expressed in terms of the MPa, while for the hardness we of the hard materials like common scales are like HRC, Rockwell hardness on scale C, as well as the Knoop hardness which is represented as HK. These are the two common parameters which are used for indicating the hardness. So, if we consider the common materials which are used as a tool material, then these properties we can have some idea about the properties of the common tool materials. So, one is like carbon steel, another is high speed steel, then cast cobalt alloys, then cemented carbides, then cermets, ceramics, then CBN and diamond. So, these are the common materials which are used as a tool materials. So, the kind of properties that these materials offer include like for the carbon steels, the hardness is around the 60 HRC, while for the high speed steel 65 HRC. For cast cobalt alloys also it is 65 HRC. For cemented carbides, depending upon the cobalt content, for high cobalt content the hardness is 1700 HK, that is Knoop hardness. Since the cobalt is a low hardness material, so when the cobalt is low, we get somewhat higher hardness of 1800 HK. Then we have the cermets. Cermets offer the hardness of 2400 HK. Ceramics of the 2100 HK. The CBN offers the hardness of the 5000 HK, while the diamond means there are two categories of the diamond. One is the natural diamond and another is synthetic diamond. So, synthetic diamond offers the hardness of the 6000 HK and natural diamond offers the hardness of like 8000 HK. So, these are hardest material is the natural diamond, while somewhat lower hardness is for the synthetic diamond. And then Knoop hardness, like for CBN it is 5000 HK. So, the low hardness is the carbon steel and the high hardness is, and then these are in the increasing order of the hardness, the ceramics, CBN and the cermets. And now if we look for their rupture strength in terms of the MPa megapascal, then 5200 means the lower hardness, higher the rupture strength is the general trend, but it may not always be true for the entire range of the cutting tool materials, like 5200 MPa for the carbon steel, then 4100 MPa for high speed steel, 2200 is for the cast cobalt alloys, and then it is 1400 for the cemented carbide, and for cermets it is 2400, for cermets it is 1700, then it is this is 1400 to 2000 MPa depending upon the cobalt content. For high cobalt content, the rupture strength is high at 2000 MPa. For low cobalt, it is low, like 1400 MPa. For ceramics, it is 1700. For alumina or like ceramics, it is 400 only, and for the CBN, it is 700. For the natural diamond and for the PCD and polycrystalline diamond or synthetic diamond, it is 1000 MPa, and it is 1500 for natural diamond. So, the rupture strength is one which will be determining which will be indicating the toughness, and so the ability of the tool material to withstand against the cutting forces, while the hardness will be indicating the ability to resist the wear as well as ability to retain the size and shape. But of course, these are the hardness values at the room temperature. More important is to consider the hardness of these materials at elevated temperature. So, if we see this list, the low hardness material like carbon steels, these will not be able to sustain the cutting conditions for long, because cutting conditions are very harsh in terms of the stresses as well as in terms of the temperature. So, considering these aspects, the low hardness materials cannot be used under the high cutting speed conditions, because they will be leading to the faster failure of the tool. So, higher is the hardness, greater will be the cutting speed which will be possible. However, there should not be any kind of interactions or reaction between the workpiece and tool material, and if this kind of reaction takes place, then of course we need to avoid such kind of combinations where the work material can interact with the tool material and adversely affect the life of the tool. Just to have idea about we know that with the increase in temperature, hardness of the material decreases. So, this decrease in the hardness will adversely be affecting to the life of the tool. So, it is important that suitable tool material is selected for a given set of the conditions, so that it can retain its hardness above the specified safe limit. So, if we assume like 40, 50, 60, 70, this is the hardness in it on the HRC scale, and this is the temperature here like 400, 600, 800, 1000, 1200 and 1400. This is temperature in the increasing temperature in terms of the Fahrenheit. So, what happens for the case of the carbon steel, it drops down very rapidly like this. This is the case for the carbon steel, while for the high speed steel it also drops, but not that rapidly, like say this is for the HSS. Then cast cobalt alloys, it maintains for the cast cobalt alloys, and then for the cermets further higher without much drop, and for the ceramics further higher without much drop. So, this is for cermets and this is for ceramics. So, what we can see here for the ceramics, cermets, there is no major drop in the hardness values with the increase in temperature. So, these can retain their hardness fairly high value, and if we assume that the minimum required hardness for the tool material for working with a particular workpiece is say this 55 HRC, then this carbon steel cannot work beyond this for this temperature. High speed steel cannot work beyond this temperature of the 850 Fahrenheit. So, means we need to work at the lower speeds when we are using carbon steel or the high speed steels, while much higher speeds can be afford the cast cobalt alloys, cermets and others can afford much higher value of the temperature without losing their hardness. So, this is important in governing the cutting speed. Higher is the cutting speed increases if the material shows higher hardness, and that is why ceramics can work at much higher speeds, like say 2000 meter per minute, while the cermets maybe say 600 meter per minute, while the cast cobalts are around 200 meter per minute, maximum 70 meter per minute for, and this is very low as like 20 meter per minute. These are the kind of speeds which are possible during the machining of the steel. So, higher is the hot hardness, greater will be the allowable speed which can be achieved through these tool materials. Now, we will come to the different options which we are available. So, these are the tool materials which are available, which offers the different hardnesses and the transverse rupture strengths, which is indicating the toughness. So, considering their hardness and the transverse rupture strengths, they are used suitably for the different kind of the conditions. These conditions include, these conditions are of the 2 or 3 types. One is like it considers the workpiece material, it considers the speed, feed and depth of cut. It also considers the tool means affects the tool geometry to be used, and then the use of the cutting fluid. So, these are the factors which will be governing the selection of the suitable tool material. Tool material selection is influenced by the workpiece, the cutting speed, feed and depth of cut to be used, tool geometry, cutting fluid and the kind of type of cutting operation, like the cutting is continuous or interrupted, like in the milling, the interrupted cutting takes place, while the turning and boring continuous cutting takes place. So, even the hard and brittle materials, tool materials can work under the continuous conditions, but if the interrupted cutting material needs to be tough. So, for the interrupted cutting conditions, it will not be good to use the very hard and brittle materials. Similarly, the tool geometry, cutting fluids, cutting speed, feed, depth of cut, all these influence the selection of the suitable tool material. Now, we will go little bit in the details of the tool materials, and so there are various tool materials like steels. So, carbon steel is one. These are normally used for very low hardness materials. Nowadays, these are not used, but still these are used for making the hand tools like the files or the saws which will be used manually. But the more commonly it is used for the more commonly used tool material is the high speed steel. And in the high speed steel, because when it was developed at that time, it allowed working with the like say 30 meter per minute cutting speed, which was much higher than what was being offered at that time by the carbon steel. That is why it was termed as high speed steel. And there are 2 variants in the high speed steel. One is the M series and another is the T series. M series basically contain these this is the molybdenum based series, and this is the tungsten based series, wherein one of the most commonly used the high speed steel of the T series is the 18% tungsten, 4% chromium, 1% vanadium and about 3 to 4% of the carbon. So, all these are strong carbide formers. So, these form tungsten carbide, chromium carbide, vanadium carbide, which are very hard and very stable, and stable means they do not soften at elevated temperature, and that is why they offer the good hot hardness. But since the tungsten is costly, so the people have tried to replace the tungsten with the molybdenum, so that the cost can be reduced. So, in that case, the molybdenum plus some percentage of the tungsten, then chromium, then vanadium plus of course carbon is added. These are cheaper, but they allow lower cutting speeds than what is possible with the T series high speed steels. These are the tool materials which soften at elevated temperature, and that is why these are not used for very high, not for high cutting speeds, and that is why these are normally used for the low cutting speeds operations like drilling, making the tools for the drilling, milling, tapping. So, these are the common tools where either cutting is interrupted or the cutting speed is low. So, not much of the heat is generated, which will be causing the rise in temperature, and which will be leading to the adverse effect on the tool life. The another one is the cast cobalt alloy. Cast cobalt alloy, basically it comprises 40 to 50% of the cobalt, then 30 to 40% of the tungsten, chromium and 15 to 20% of the tungsten. This mixture is melted, and then in the graphite mold it is poured, so that by casting route the tool is made. So, it does not require any heat treatment to achieve the desired hardness, but in case of the high speed steel the heat treatment is needed in order to achieve the desired hardness of the 65 HRC, so that the surface of the HSS can be hardened while the inner portion of the tool remains tough, while the surface is hardened through the suitable heat treatment. So, these are the this is what is about the cast cobalt alloy. Cast cobalt alloys are found somewhat compared to the cemented carbide. If we talk of the cemented carbide tools are basically the cobalt tungsten carbide. These are the two main constituents, wherein the cobalt concentration may vary 3 to 6% in the low cobalt category, and in the high cobalt category it may be 6 to 12%. So, accordingly we get the higher hardness or the lower hardness. Cobalt is used as a binder, while the tungsten carbide particles will be there as a reinforcing agent, and these are produced through the powder metallurgy route, wherein the elements in powder form are compacted, then sintered to get the shape in the desired form of the inserts, so that they can be used for the cutting purpose. If you see with regard to the properties, the cast cobalt alloys actually fall in between of the cemented carbide and the high speed steel. So, accordingly the hardness and the toughness of the cutting speed of the cast cobalt alloy falls basically between the high speed steel and the cemented carbide tools. So, cast cobalt alloy normal cutting speed is around say 80 to the 200 meter per minute, while 200 to 600 means on the higher side is used for the cemented carbide, while 30 to 60 is for the high speed steel in terms of the cutting speed meter per minute. Now, we will talk little bit more in details of the cemented carbide tools. Now, so in the cemented carbide tools, basically there are two broad categories, one which are used for the steels and those which are for not for steels, or they are used for like say the non ferrous metals. So, the cemented carbide tools are basically for the steels and for the steels, not for the steels category. These are the two broad categories. So, those which are used for the steels are modified with the titanium carbide and tantalum carbide plus tungsten carbide. Cobalt is used as a binder, and the percentage of this titanium and tantalum carbide is around 12 to 25%. While so these when these are used, it reduces the wear of the cutting carbide tool insert or cemented carbide tool insert, especially in case of the during the machining of the steel. So, if we use the straight tungsten carbide cobalt base cemented carbide tool, which is like cobalt and tungsten carbide, during the machining, actually the machining of the steel which is having iron. So, iron actually interacts with the carbon in the carbide of the tungsten particles. So, this interaction leads to the instability of the WC. So, the carbon is lost and it is left with the tungsten only. So, the surface near surface layers basically become depleted of the tungsten carbide particles. So, they lose their hardness, and so this region is subjected to the very sharp wear, and that is why crater is formed near the cutting edge in this form. So, the straight cobalt tungsten carbide type of the cemented carbide tools, when used during the machining of the steels, it results in crater wear due to the diffusion of the carbon with the iron or with the steel, leads to the loss of the carbon from the rack face of the tool, which in turn promotes the crater wear. That is why the straight tungsten carbide straight tungsten carbide cobalt inserts are not used for machining of the steels, but these need to be modified with the. So, when the modified version TIC and TAC modified version of the COWC inserts are used, it offers the good tool life, while for the non ferrous metals we can use the straight WC and the cobalt tungsten carbide cobalt type of the tungsten carbide cobalt type of the cemented carbide tools. So, a little bit more in details, there can be different categories like high alloyed WC CO insert. These are used for machining of the ductile metals, cast steels, as well as cast steels, ductile metals and alloy steels. So, these are basically cobalt, TIC, TIC, TAC, WC, high in concentration of these TIC and TAC, while the low alloyed WC CO insert wherein the concentration of the TIC and TAC is somewhat less. These are used for machining of the cast iron, as well as these are also used for machining of the cast iron, as well as somewhat soft grades of the steels. This is represented by the letter P, and it is coded by the blue color, high alloyed cemented carbide inserts, while the M code is used for the low alloyed tungsten carbide cemented carbide inserts, and it is coded with the yellow color, while the K letter is used for the cobalt based inserts, which are used for the non ferrous metals, coded with the red color. These are basically straight cobalt tungsten carbide inserts, and these are used for the non ferrous metals. So, here like say if we see the typical cemented carbide insert, then you will see these are the carbide particles fitted with the cobalt matrix. Cobalt matrix can be 3 to 6% or 6 to 12%. So, when the cobalt is high, we will see that hardness is less, and that strength and rupture strength is high. But the size of these particles also is important. The fine size of the particles, means the carbide particles, reduces the hardness but increases the transverse rupture strength. So, this is how the properties vary, and these particles are generally are used in the size range of the 2.5 to 12 micrometers. So, these are very fine in size, and these are used for making the cemented carbide inserts through the powder metallurgy route. There are three more common tool materials which are also used in the metal cutting. These are the cermets. Basically cermets, although cobalt and tungsten carbide is also cermets, but in the cutting technology these are not used as a typical cermets. These are not termed as a typical cermets tool materials. So, for the cermets basically TIC, TIN, titanium carbide, titanium nitride and titanium carbonitride are the commonly used cermets for making the tool materials. And these are these powder form, these materials in the powder form are mixed with either cobalt as a matrix or nickel or as a matrix, the nickel as a matrix or the molybdenum as a matrix. So, these are the reinforcing agents, and the matrix is either of the nickel or of the cobalt. Since they have very low rupture strength and very high hot hardness, so these are primarily used for the finishing purpose, and when working with the high cutting speed, low depth of cut and the low feed. So, these are the favorable conditions when cermets can be used. Then we have the coated carbide tools. Coated carbide tools are basically the cemented carbide tools, means these are like WCN cobalt base cobalt type of the straight tools, which are usually coated. Coatings are made either of the TIC or TIN or means titanium nitride, or it can be coated with the alumina also. But to have so when we coat in, these provides the good stability at elevated temperature as well as good wear resistance. So, they can be worked at much higher cutting speeds, but in order to avoid any kind of the chipping off or of the spalling or the separation of the coating from the tool material, normally the bond coat is given. Bond coating is provided of the either TIC or the TIN, because these two because these two materials have very alpha value or thermal expansion coefficient similar to that of the cemented carbide tool. So, there is no mismatch in terms of the alpha value, and that is why it results in the very good bonding with the substrate, that is the cemented carbide tool, and over this we can deposit number of the other coatings as per the requirements for developing the multi coated carbide tools. So, they will be performing much better as compared to that of the simple straight plain carbide tools. So, because of this coating helps in making the cemented carbide tools to work at much higher speed with the much better feed and the depth of cut, especially for the finishing purpose. Also, these can be used for the machining using moderate level of the feed and the depth of cut. Other two materials which are there in like ceramics. Ceramic basically this is alumina based, where alumina particles in finer powder form are compacted and then sintered to make the tool through the powder metallurgy route. Sometimes with the alumina, zirconium oxide is also added, so that the properties can be enhanced further. Because of their low transverse rupture strength, these are not used for high feed, not for the high feed or high depth of cut, high DOC, but definitely these are used for the high speeds, especially for the finishing operations, not for the making much of the cutting. Then another one is the diamond. Diamond is basically like sintered polycrystalline diamond, or these are also known as PCD, polycrystalline diamond, or sintered polycrystalline diamond. These are the two things which are normally used. These are normally used for developing the coatings of about 0.5 mm, and since these are very good in terms of the hardness as well as ability to withstand at the high temperature. So, these coatings of the PCD can be effectively used for machining of the non-ferrous metals. So, like the glass, graphite, plastics, etc., can be easily at very high speed machined, but these are not used for diamond coated tools, or the diamond inserts are not used for machining of the steels as well as the nickel base alloy, because the carbon has affinity with the steel as well as the nickel alloy. So, by the diffusion the coating loses the carbon, because the diamond is basically one form of the carbon. So, the loss of the carbon to the steel and the nickel alloys, the tool life is adversely affected during the machining of the super alloys, nickel alloys, and the steels using the PCD or the sintered polycrystalline diamond. That is why these are not used for machining of the steels, iron, or the super alloys. On the other hand, the CBN, that is cubic boron nitride, also offers very good hardness, and therefore, CBN, cubic boron nitride, becomes especially inert to the steel as well as nickel alloys, and that is why this is a very good option to replace the diamond as a cutting tool material. And but the cost of the CBN is very high, that is why it is economically justified only when this is economically justified only when the volume of the production is too high, or we need to work at high cutting speeds, so that we can afford the cubic boron nitride effectively. Now, I will summarize this presentation here. In this presentation, I have talked about the kind of the material properties which are required to make the tool, so that it can perform effectively, apart from what are the various options available in terms of the tool materials and under what conditions they can perform. Thank you for your attention.